Welcome to The Explainer. So today we're going to tackle a really fascinating design challenge. How do you build a mechanism that moves in one very specific way, and only in that way? We're going to explore a super powerful framework that lets us actually design from the motion back to the machine. Think about it. If you're an engineer, you usually look at a machine and you try to figure out how it moves. But what if we could just flip that entire process on its head? What if, instead of analyzing what's already there, we could work backward from a perfect, desired motion to create the perfect machine right from scratch? Okay, so let's really dive into this whole idea of designing in reverse. This slide just captures that shift in thinking perfectly. See, on the left, you've got analysis. That's the forward problem. You're given a structure and you figure out its motion. But on the right, that's where we're headed today. Synthesis, the inverse problem. We get to start with the motion we want, and from that, we derive the exact structure that will produce it. We're literally shifting from being analysts of what exists to being architects of what we desire. All right, so here's our game plan. We're going to start with the core idea of designing in reverse. Then we'll look at the systematic algorithm that makes this all possible. After that, we'll apply it to a real-world example, see what happens when it has limitations, and finally we'll wrap up by understanding why this method is just so incredibly powerful. First up, designing in reverse. To build any complex structure, I don't care if it's a skyscraper or a tiny precision mechanism, you need a fundamental building block. You need a simple, reliable component that you can use to build up your more complex designs. And here it is. This is our fundamental Lego brick, the ideal wire flexure. Just picture a thin, slender rod. It's incredibly stiff along its own length, right? So you can't push or pull on it. But it's totally flexible in every other direction. In engineering speak, this gives us a pure translational constraint. It's basically like putting up a wall in one and only one specific direction. This simple little component, it's the key to everything that's going to follow. So we've got our building block. Now we need the instruction manual. This section is all about the systematic algorithm, the step-by-step procedure that lets us translate a motion we want into a physical structure built from those wire flexures. Before we get buried in the math, let's just talk about the process in plain English. It's pretty straightforward, actually. First, you have to precisely define the motion you want. Second, you figure out all the forces and torques, the constraints that are reciprocal to that motion. And that just means they'll cancel out any movement you don't want. Third, and this is crucial, you make sure you can actually build those constraints using our wire flexures. And finally, you pick the exact set of constraints that will become your final design. And here's what that looks like as an official algorithm. It's a formal, four-step process, and it's all grounded in this really cool idea called the rule of complementary patterns. All that really means is that for any system, the ways it's allowed to move and the forces that are restricting it are basically mathematical opposites. They're reciprocal. So by solving that little equation you see down at the bottom, we can systematically find the exact set of restrictive forces we need to achieve pretty much any motion we desire. Okay, this is all great in theory, but does it actually work in the real world? Let's make this tangible. We're going to use the algorithm to design something simple and elegant, a compliant slider. That's just a mechanism that can only move back and forth along a single straight line. Step one is to define our goal. What do we want? We want a mechanism with exactly 1 degree of freedom, pure translation, just along the x-axis. No wiggling, no rotating, nothing else, just sliding. Now, in our 3D world, there are 6 total ways something can move. So if we want to allow just one, that means we have to restrict the other 5. So our puzzle is to find 5 independent constraints to make this happen. All right, next, we apply the math. Step 2 uses that reciprocity idea to find the general mathematical form for any constraint that we work with our sliding motion. Then, in step 3, we add another rule, the pure force condition. This is what makes sure that these constraints can actually be built using our ideal wire flexures. What we're left with are 2 final equations that any valid constraint has to obey. Now that we've got our rules, we can pick a specific team of 5 constraint vectors that follow those rules. You can see one possible set right here. These 5 vectors, or wrenches, all work together to create a constraint space that perfectly cancels out all motion except for that one translation we want along the x-axis. And here it is, the payoff. This is where the magic really happens. Those 5 abstract mathematical vectors from the last slide, they translate directly into physical, manufacturable designs. It turns out there's more than one way to arrange them, but just look at design 3. Those two parallel sheets, that's a classic go-to engineering solution for precise linear motion. And we just derived it from first principles using nothing but pure math. How cool is that? Okay, this seems like a perfect system, right? A guaranteed way to build any motion you can possibly dream up. But like with any powerful tool, it's really important to understand its limits. So this leads to the big question. Can we really use this method to build any motion we can possibly imagine using only our simple wire flexures as the building blocks? And the answer, maybe surprisingly, is no. This is the big reality check. Sometimes the math works out perfectly on paper, but it asks for a type of constraint that our simple wire Lego brick just can't provide. The algorithm might say you need a screw constraint, which is like pushing and twisting at the same time, or a pure couple, which is just a pure twisting force. A single wire, well, it just can't do that on its own. For example, let's say we want a mechanism that can slide freely along the x-axis and the y-axis, but do absolutely nothing else. It's a perfectly valid motion to want. The problem is, if you run this through the synthesis algorithm, you discover that there is no possible arrangement of simple wire flexures that can create the necessary constraint pattern. So while it's mathematically valid, it's physically impossible to build, at least with the simple tools we've given ourselves. So given that limitation, what's the ultimate takeaway here? What does this powerful design framework truly give us at the end of the day? The real power of this whole method is transformation. It transforms the creative and, let's be honest, often frustrating challenge of designing a mechanism from a process of intuition, guesswork, and trial and error into a solvable linear algebra problem. We get to move from that messy sketch on the left to the clean, predictable, and mathematically guaranteed result on the right. And what that really means is that for a huge class of motions, we now have a clear, predictable, and guaranteed path from an idea in our head to a working mechanism in our hands. It completely replaces ambiguity with mathematical certainty, which is pretty much one of the highest goals you can have in engineering. And that kind of leaves us with a final thought to chew on. We've just seen a blueprint for turning abstract mathematical desires into concrete physical reality. So now that we have this blueprint, what new worlds of motion, what new kinds of incredible machines will we choose to build next?